Just a reminder, in case you did not see this recently, there are announcements about online office hours. If you haven't seen this already, I know many of you have already been participating in online office hours, but Allison, our Friday Reputation Leader, has online office hours in the evenings on Thursday and Saturday. Well, afternoon on Saturday, I guess. The office hours list on Canvas has been updated to reflect that as we approach our first exam, which is Friday in class, next time you're going to be here. You might want to think about utilizing some extra office hours between now and then. I have office hours today right after class. There's Barbara's got office hours in the Tutor Center this afternoon from 2 to 4 in the HAV Hassayampa building, 4:30 to 9. There's some tutors there as well. And then all day tomorrow, you can see the whole variety of office hours tomorrow. So if you have some additional questions that you want to go through, whether it's homework questions, oh, and I did fix the homework 3, by the way, so you can go back in and review it, the iMath AS homework. If you have additional homework questions that you want to go over, if you have just questions from the list of items to study, remember that there is a list, let me get back to it, at the end of Module 1, you'll see there's topics outlined for Exam 1. Please take a look at that. This covers what you need to know. So stuff about variables, parameters, and constants, constant rate of change, a whole bunch of different things to think about related to that. That's our main overall concept. But related to that are functions and their graphs, graphs of functions, and function notation, and how you can use that in a variety of different ways instead of just expressing, plug something in and get a result. All the different ways we've used that to express the dependent variable values, whether or not we know a number that corresponds to that or a formula to calculate it. So make sure you look over this list of topics for exam number 1 so that you're set for Friday. Also, on Friday, this is our first test. All of our tests will be kind of the same except for the derivative mastery test, which is not multiple choice. We have multiple choice tests on a Scantron. I'll bring the Scantrons. What you need to do is bring a pencil, not a pen. Pens don't work. I need a pencil. And bring a photo ID and know your student ID number. If you have an ASU ID card, that serves both purposes. On the Scantron, you're going to have to fill in your name and your student ID number. I need you to know your student ID number. If it's on your photo ID, then great. If it's not, just make sure you know it someplace. Write it down on a piece of paper if it's not something you have memorized. But since there are a lot of us, we don't all know all of you by sight. We're all going to be collecting tests. Just bring a photo ID. You can double check who you are. I hope you don't change people during the course of our class. But in any case, that's Friday. The test will be limited to just the class period. I will be here a little bit early just to make sure everything's set in here. I'll start passing out Scantrons a little bit before class starts. If you're here, that way you can start bubbling in your name and all that and not be spending time doing that during our 50 minutes. The test might not take you 50 minutes, but I do want you to have the whole time period if you do want it. It's only like 20-ish questions long, and it is multiple choice. There's not computations that you're going to have to like divide decimals and find square roots by. It's not about computation. It's the same sorts of questions you've had in the homework and the quizzes, other than there's not essay questions. Things formulated as multiple choice. Like, is this a variable, constant, or parameter? Instead of being you write the word, it's multiple choice. Or which of these describes why this is a function, like you did on your last quiz. Instead of you writing out a sentence, why is this a function? So those sorts of changes will be made from how you've answered some of the questions before, but all the same topics as things we've discussed. So no new information completely that you're going to have to come up with out of the stars. It's stuff that we've talked about. So make sure you look over the list and understand what the topics are expressing to you and how we've used those in quizzes, in activities, in homework, just in discussion. Rewatch the lecture videos if that's helpful. Reread your notes if that's helpful to you. Meet up with some people. Go to office hours. All right, so what I want to do today then is just kind of continue with the summary of stuff that we did and maybe extend a little bit farther. So on Friday, long time ago now, we were talking about going back to our flag example, and I know I put these questions up at that point in time, asking you to think about at least A and B I had up. asking you to think about what these are asking you to determine. Is it a y or a dy or a dx computation? So make sure when you're looking at questions like this on quizzes, tests, homework, anything you're working on, when you're asked to describe something, express something, calculate something, make sure you know what is that quantity called that I'm trying to find, other than just the height of the flag. Would that be in this situation in terms of my variables for part A? We've got x representing elapsed time in seconds and y representing the height of the flag in feet. This is kind of abbreviated from, we did this before. Elapsed time in seconds since the flag began lowering from the top of the flagpole. So if the flag began at 110 feet above the ground and we're asking how much had it lowered after 3.72 seconds, what quantity did we decide this was asking us for? X, dx, y, or dy? If it's how much has the flag lowered after 3.72 seconds? That's a dy. It's not a value of y, right? Y is asking for what is its height, and A, this is a dy. It's asking how much has its height changed? How much has it lowered during 3.72 seconds? So yeah, this is asking us for a value of dy. So if I want to calculate dy, or if I want to express dy, maybe not actually do the computation, but if I want to figure out what this change in height is, I've got dy, and I've got a constant rate of change of 0.75 feet per second. After 3.72 seconds, 3.72 seconds is a value of dx, how much the time has changed, in this case since the start, so it would actually also be a value of x. But this is an amount of change in time, and this how much it lowered during those 3.72 seconds is a corresponding value of dy. So my dy, the thing I'm looking for, would be m times dx. So I don't use this 110 for anything, just the m. Well, m isn't exactly 0.75. M is really negative. We decided it's lowering by 0.75 feet per second. So my change in height would be negative 0.75 times 3.72. Saying this in a sentence as opposed to in a math expression, I might not say negative. I could say that the flag lowered by 0.75 times 3.72, whatever that comes out to. What would the units be on this? The units for this dy would be a number of feet, right? So this is a number of feet. I don't have to calculate it to know that that expresses how much it lowered, so I'm not going to go through that right now, but this is a number of feet, and it's the number of feet that it changed by. That's why it's allowed to be negative. So what about part B? What is the flag's height, its height, after 12.87 seconds? This is asking for a value of x, dx, y, or dy. Y, right? And we have, that's, if I'm looking for a value of y after a certain amount of time, that means I'm looking for a y final. So I need to know an initial height and a change in order to calculate that. So where did the flag start? 110 feet plus our change. Well, our change is going to be negative, so if you're plotting in advance, you can say minus instead of plus and then a negative number. But our change is kind of like this, but a different number of seconds, right? The time varied by 12.87 seconds, so the height will decrease, vary in a negative direction by 0.75 times 12.87. So our starting height, and then plus this change in height, or starting height minus how much it lowered during that 12.87 seconds. And we could compute that, but this would be how we'd express it without needing to do the comp. I don't have to know any other facts. This would be enough, and if we really needed the answer, calculators can do the grunt work for us. Yeah.
So then for the exam, would it have like an expression like that?
Yeah, so you might see this good example. So on the exam, like I said, there's no calculators on the exam. If you're asked to write something, it might just be write it, which expression, multiple choice, which expression represents the height of the flag after, and you might see something that looks like it's actually a calculation for dy versus something that looks like a calculation for y final. But it wouldn't be a worked out decimal number. I don't want you to be spending time doing weird decimal multiplication. There might be something where you need to do 2 times 3, but there's not going to be anything that I would expect you really want a calculator for. All right, so what if I wanted to, part C, describe the flag's height y after any number of x seconds where x is between 0 and 100. Not meaning I need you to calculate what it is at 0 and 100, but just after a certain point in time, the flag's going to hit the ground, so this wouldn't be valid. So just imagine we're in a reasonable domain here during the flag ceremony while the flag is lowering. If I wanted to describe the flag's height at any general number of x seconds since the beginning, well, that means I'm looking for an expression of the flag's height, not of how much the flag's height changed only, but of the initial height plus the change. So it's most like part B, the only difference being we don't know how many seconds, just a general number of x seconds into the ceremony. So if I want to describe the height, I'll write y equals. So this would be our final height at any point in time. It's going to be the same as the last one. We start at 110, and then we subtract 0.75 feet for every second that goes by. It's just, well, I want to express this for any number x, not just 0 and 100, but anything within the ceremony. What could I put in that spot? There's a couple of different ways you could write it. Yeah, I could just write x, but what is this x representing? Yeah, it's the time that elapsed since the start. So just kind of like we talked about here, this 3.72 is dx, but it's also the same as x since we're measuring from the beginning or since we started the ceremony. If we're looking at the ceremony started at time 0, you could write just x here, or you could write, well, I really want to know how far x is past 0. It happens to be past 0 in this point. So I could write x or x minus 0. Obviously, those are the same. But not all the time does our reference point, we're starting at time 0, the flag was at 110 feet tall. We don't always have to start at time 0 or at x equals 0. We could start someplace else and do the same types of computations, right? We shouldn't have to change our process entirely because we're not starting at this constant rate of change at a time 0. We can start from any point in time, as long as we know how to express the variation in time where it began. Yeah?
So if the domain was 10 to 100,
Mm-hmm.
the formula would have to be 110 minus 0.75 x minus 10.
Right, so I have an example about that next. So a reason why we might start at something other than 0. But yeah, if it wasn't time 0, we just put in some other number here other than 0 for when that constant rate or from when that evenly measured descent began. So let me erase this. All right, here we go. Here's our good reason. So we're trying to start our ceremony. There's a wind, chain gets tangled, they're fussing with it for a little while. So it's not really even descent over the first 20 seconds or so. But after that, we're able to keep a constant descent rate of this 0.75 feet per second. So let's say that it took a while, but after 20 seconds we got down to this, the flag was at 104 feet when finally we were able to keep the nice even flag ceremony going. So if I wanted to answer questions about how much this flag would descend in the next 3.72 seconds, same numbers I used last time, after we're going at this nice constant pace, what do I do to compute this descent during the next 3.72 seconds? Same thing, right? Negative, this is still asking for a dx. or this is a dx, 3.72 seconds. Yikes, stop. There, give you a preview of the next question. This is still dx. It's just not also x in this case, because it took a while. From time 20 to 23.72 would be the interval we're talking about. So this is dx, but no longer x. If I want to know how much the flag descends, it's still the same computation as before. At this point in time, and during the 3.72 seconds between time 20 and, well, the next 3.72 seconds, the flag's descending at a nice even rate of negative 0.75 feet per second. So we have this expression for dy. dy equals mdx. During this interval of 3.72 seconds, we have this nice even rate at which the flag is descending. So it doesn't matter that it's not the first 3.72 seconds. We've got, if I've got constant rate of change, a change in my dependent variable is a constant multiple of a change or variation in my independent variable. So regardless of when this variation happens, I've got the same rate and the same resultant change in height. So if I wanted to know what's the flag's height by 23.72 seconds, like by the end of that next 3.72 seconds, this is asking for a y final, right? What is the flag's height? Not how much did it change, but what is the height? That's our y final is our initial height plus, well, dy. And we know that dy is also mdx. So all we need is our height at the beginning plus a change. And our height at the beginning was what this time? 104. So my new height, my height by time 23.72 is going to be my height, and I'm going to change this to function notation in a minute, is going to be my initial height plus a change. It went downhill by 0.75 feet per second for 3.72 seconds, not downhill, down the pole. So it doesn't matter that the 3.72 seconds weren't at the beginning. The 3.72 represents a change in time or time passing by that much. The flag lowers by this amount, whatever that comes out to be, 3-ish feet during that 3.72 seconds. So it would be closer to 101 feet by the time we're done. All right, now what if I wanted to know part C? Yep, sorry. 23.7, oh, so 23.72. This is my time at the end of the interval. So what would the flag heights be by this time 3.72 seconds later? So in other words, at time 20, the flag was at height 104. By time 23.72, we're trying to express the height of the flag. So what's the 23, how is the 23.72 built into this? We didn't write it out. Yeah.
It's like the 20 is the 104, and the 3.72 is the change.
Right, so dx, in the first problem we didn't really calculate it because we started at 0, and in the first 3.72 seconds, the flag lowered by a certain amount. So that was time 3.72 to 0. But dx is x final minus x initial, right? How much time has passed or how much time we're varying through. So our dx is kind of built in here. This 3.72 is how much, the 23.72, which I kind of mentioned when we were doing part A, minus 20, x final minus x initial. So between time 20 and time 23.72, that's the 3.72 seconds we were talking about. So the dx is still that 3.72. During that specific 3.72 seconds, the flag lowered as much as it would during a lot of other 3.72 second intervals. It doesn't really matter when they were, other than it was while the flag was being lowered at a constant rate, so after time 20 and before it hits the ground. Yeah.
So, your initial time starting at 30 seconds?
So the flag started lowering from 110 feet, and it got tangled up for a little while, but by time 20, we were able to continue a nice even rate. So the constant rate doesn't apply until after time 20. So graph speaking. So if I were to try to graph the height of this flag over time, thinking about this. So let's say I have x, which I'm using here as time in seconds since the flag started lowering, not since time 20, but seconds since the flag started lowering, and the height of the flag in feet since the start of the ceremony. So at time 0, the flag was at 110. So that's one correspondence point we had from the last slide. It's not listed here anymore, but it started at 110 feet. We're trying to lower it at a nice constant rate, but for the first 20 seconds or so, there was some wind, it got tangled up, maybe we were fussing with the chain and it went down quickly, then slowly, and we're trying to get it. And then finally, at time 20, when the height's 104 feet, we're able to lower this at a nice constant rate. So after time 20, we start lowering the flag at a nice constant rate, where for any change in time, any variation in the time that we have, the corresponding change in the height of the flag is in the opposite direction, 0.75 times as much. During that section. During the first part, we don't really know what was happening. Maybe it was kind of close and jumped around a bit. There was wind, the chain got tangled, whatever. But then we got settled in and went at our nice even flag ceremony after that. Does that make sense? So that, graphically speaking, you can see constant rate of change by, like, if I were to take that triangle, I could slide it up and down that section of the graph. I could also make the triangle like larger and smaller, similar triangles that would have the same ratio of side lengths. If dx got a little bit larger, dy would get, well, larger in the opposite direction by a factor of 0.75. Or if I made dx smaller, that dy would still maintain the same ratio. It'd still be that constant multiple. So I could move it around on that line segment. I could also make it larger or smaller, triangle. So I'm going to clear this all off first a bit. Oh, yeah.
Reverse to question A.
Mm-hmm.
The question asks how much will it descend in the next 3.72 seconds? Will it be 0.75 instead of the negative?
Right. Yeah. So
Negative?
to compute it, to compute the value of dy would be a negative number. But if you wanted to say it in a sentence, for sure, you'd probably say how much did it descend? You'd just say it descended by 3 feet or something, not -3, right? You wouldn't want to say it descended by a negative number of feet. Correct. All right, so let's take a look at this last question then. So keeping this all in mind, and we're going to take a look at more graph stuff today. If I want to know what's the flag's height at 45.31 seconds into the ceremony, assuming that it's not on the ground yet. So remember, we have our two key facts, y final. A y value depends on where we started, and a change in y, where the change in y, in this case, during this post x equals 20 category, has a constant rate of change to x. Y has a constant rate of change with respect to x, or dy is a constant multiple of dx. Variations in x multiplied by the same number, -0.75 here, give us the corresponding variation in y. So if I want to answer this question, what is the flag's height at 45.31 seconds into the ceremony? Am I looking for a y or a dy? It's something about flag height, so I know it's not an x. Yeah, this is looking for a y value. I'm trying to find a y value somewhere into the ceremony. I know the y values earlier, so let's think of this as y final. I'll write y final. You could just write y. But to compute that, or to write an expression that will compute that, all I need is some starting height and how much I changed in the intervening number of seconds. All right, so if I have a starting height, any other height that I know when it happened. At 104 and time 20, I know that happens. So I have a starting height of 104. This is the height at time x equals 20. I need to know how much the height has changed since then. So I need an mdx sort of expression. dy, I'm going to replace that with mdx. Well, the m part's that constant rate of change. What's dx? How much has x changed since then? Since the height was 104, how much has x changed? Right. This was at time 20. We're looking at something 25.31 seconds later. So I could write 25.31 here, but where that comes from, that's dx. This is x final minus x initial. And since we're looking for y final to be a height at time 45.31, 45.31 must be my final time. And the starting point we used, the reference point, what we were measuring from was this at time 20, the height was 104. Oh, well, we've changed by 25 seconds since then by subtracting these two. So since this height 104 happened, 25 something seconds have gone by. That's how I'm going to compute my new height. Oh, my starting height plus what happened over the next 25.31 seconds. Because this time is later than the starting point that we had by that much, 25.31 seconds. The height will vary by something else. And I honestly don't know what the new height is, but it should be lower, right? After 20-something seconds, our height will lower by, I don't know, 17, 18 feet, maybe, just taking a guess. So this will be somewhere around 80-ish feet if we do the computation, just as a, yeah, should be something lower. But if you get stuck with something, like, all right, well, what would the flag's height be at, well, we know it at 20 seconds into the ceremony. What would it be at 21 or 22 or 30 or 35 or 40? Think about what is this pattern? Oh, every second, here's our basic definition. Every second, the flag's height lowers by 0.75 seconds. For any number of seconds, did I say seconds? Lowers by 0.75 feet. After any number of seconds go by, I can find the number of feet that we vary by, that the height changes by taking that number of seconds times 0.75, making it in the opposite direction, or times negative 0.75. Just make sure you interpret carefully with negatives. All right, so let's take a look at a graph. And let me clear this off. I'm going to pull up a GC picture. Maybe. Oh, I've got my, there we go. All right, let me make this go away. So if I have this very, very general picture here, here's just, I'm starting at some initial point. I can't do subscripts in this, unfortunately. X, I, Y, I. So X initial, Y initial, starting at some point. And I've got XI, you can see that just stays at one position on the horizontal axis. X moves. What sort of thing is XI? Constant variable parameter. Yeah, it's a parameter. It's not changing. It's something right here. I could change it and do a different problem. I could make it appear someplace else. But in this situation, it's not changing. I don't know its value. It's not something I can look up. X initial is always 7. And I don't know what it is. But I've got X that's varying. I can see there's a Y value that corresponds to this X as it varies. And the relationship between the two of these, I can see, well, as X changes by dx, this maintains this constant rate of change relationship. The Y increase in this case is always m times as much as that increase in X. Yeah?
So how you select xi as a parameter, where xi is, if it would say 7, that would make that a constant.
Yeah, if this said 7 comma yi, yeah,
So
then
parameter-
7 would be a constant.
So parameter, this is like the constant of letter.
Yeah, parameter is something. So a parameter you can, it's a symbol. So it's not going to be a 7. It's a symbol that you can use in a situation and leave it alone. It doesn't have a domain to it per se, but you could reconceptualize the problem and make it have some other fixed value. Like I could draw it someplace where obviously I know it's negative, but it's not a known particular one value only. So this xi is just standing for one particular number that I don't know or I don't care what its value is, but it's just, think of that as a starting point. Regardless of what maybe happens before that, maybe this is like the opposite of the flag ceremony. Now we're putting the flag back up the pole. And the first bit, it takes a while because you've got to get everything connected and somebody's holding on to the back of the flag, and then you start raising it at a constant rate. So whatever happens initially, during this phase of this graph, I've got a constant rate of change relating x and y, or y has a constant rate of change m with respect to x. So if I were to look at something like this and want to describe, let me make this a little bit bigger. Actually, let me make this not full screen, maybe. Hi. Now I'm stuck. There we go. Come on. Let me just make this bigger this way so I can fuss around with my writing. All right, so in this picture, I made this changeable. I made my rate 1.7. So I've defined a parameter, rate, which I can change and make the picture look different. So I can make it 3.75, and there's some computations down below. And now it looks bigger. But within this diagram, let me scoot this down a little. Nope. There we go. As this plays, the rate, 3.75, isn't changing. It's staying the same throughout this picture. I can change it and have a different picture, but as this animation occurs, the rate isn't changing. It's one rate throughout. So let me stop this for a second. There. All right, suppose I wanted to just, in general, describe y final, the y at the end of this, the one that's moving up the line that I've stopped suddenly, just in terms of x and the parameters in this graph. So you can use 3.75 instead of using the parameter m. So m is a parameter, 3.75 is a constant. So m right now has a value of 3.75, but I can make it something else. 3.75 is a number that we all know what it is, more or less. So if I wanted to just describe, maybe, there we go. Just describe the y value here in terms of this y, in terms of what I see in the graph. Think about what we did before. So y final is our y initial plus m dx, right? That's our really super generic way of writing this. So there's not a dx that's a measurement here, but I have dx here. Is dx a variable or a parameter? Yeah, dx is a variable. Remember when this guy's playing, that dx gets larger and mdx gets larger. So dx is a variable. It indicates a variation from x initial to the current value of x. So if I want to express y final just in terms of x and the parameters seen in the graph, that means I don't want to use dx. How could I restate dx in terms of parameters and variable x instead of using the variable dx? Yeah. Yeah. dx, if I want to compute how big dx is, I need to know how far apart these two x values are, how far x has passed our initial x value. So if I wanted to follow the instructions here, y final is y initial plus m, and then which one do I put first? Yeah, in this picture it'd be x minus x initial, because x is larger if I want to express that change. Now, realistically, what if this was going the other direction? That would just mean this dx would be something negative, and then m times that would be something negative, because m here is positive in this picture, which would mean I've taken my y initial and then adding something negative. But if if this subtraction is negative, that means that x is to the left of xi anyway. That's okay. So in reality, it doesn't matter. As long as that fits within the domain of whatever problem we're doing, it's okay if this subtraction comes out to be something negative. It would just indicate that you're moving to the left of your initial position on the independent variable axis instead of to the right. And that's okay. So, let me move this just a little bit farther this way. All right, so suppose that, actually, let me change this around. All right, moving this graph to be at a different location. So, there we go. Sometimes writing that general case, because it's the same every time, dy plus mdx, or dy equals mdx, and y final is y initial plus mdx. You can kind of just repeat that. Make sure you know those, by the way, but think about how it applies to specific situations in your head. So if you have some numbers, don't let that throw you off and think you suddenly have to do something entirely differently because there's a number instead of a parameter xi or just a dx, something like that. So for instance, suppose I have a rate of 3.75, which I do right now. If I wanted to write this more specifically instead of what we just wrote a minute ago, all I'd have to do is change, instead of writing y final is y initial plus m dx, I'm going to write plus 3.75 dx, where we said the dx was x minus x initial, right? So see if you can take our general situation and do versions 2 and 3. I'll make the pictures match when we do them, but take a minute or two. See if you can write your y equals y initial plus m dx. General expression for version 2 and version 3. I'll make m look like negative 0.75 in a minute, if you want to see that. But when you have more numbers, don't let it throw you off. When you have a constant rate of change, the same facts hold all the time. There we go. So here's the picture with our negative rate. So our negative 0.75 we use with our flag, right? So you can, if you want to go back and think about, like, if there's not a story and you've got a bunch of symbols, make up a story like, oh, so we've got a flag starting at 12 feet high, going down by 0.75 feet per second. If you can relate examples that are general, no context, back to something that you've worked through before, you can maybe help yourself think through to an answer like, what does this mean? If there is a story and you don't like it, change the story into other topics. But this is, oh, this isn't starting at 12 feet high. What is this? What would this 12 be in terms of the flag story? Time, yeah, that'd be time 12. So at time 12, we start decreasing by 0.75 feet per second, or make up your own story. But this is the independent variable starts at 12. So 12 down here, and let me get this back to writing. So this is starting at time 12. And at that point in time, I don't know what my y value is, but this is at point 12 comma something. And as x changes, the rate of change of y with respect to x is negative 0.75. So as x moves away from 12 or varies past 12, then my y value is going to decrease from wherever it was. We don't have a number for that one. But then this should just look like, well, my y value, y final, started at who knows what, and decreased by 0.75 somethings, if you want to make it a flag story, decreased by 0.75 feet per second for however many seconds we've passed. Well, we're starting at 12 and going onward. So my x value, in this picture, you can imagine it larger than 12. So x minus 12 is our dx expression. But in reality, it doesn't matter if x is larger than 12 or smaller than 12. If you want to think about if this were the flag ceremony, as long as before 12 is a valid point in time, I can't make the animation do this. But if I were to imagine x getting smaller, then just if I'm past some point in time, then the change in y is going to get smaller. If I were to go back up this line, the height of the flag would get bigger than it was at time 12 if I were to go backwards in time from them. And that's okay. Just like the question on the quiz that you had. W, the weight of the barrel with the water in it, isn't allowed to be negative, but dW, a change in the weight of the barrel, is allowed to be negative. So whether that's the independent or dependent changes can be positive or negative, typically speaking. The actual variable values, less often are both of those acceptable. But in any case, I can decrease the amount of time that I'm thinking since the start of the flag ceremony and thus increase what the height is. Even though time doesn't run that direction, I can imagine what if I were to go back in time, how high would the flag be? We shouldn't be able to calculate that. So last version here, suppose we have a rate of 2, rate of change of y with respect to x. I'm just going to change this up here so it looks like that. There we go. And get rid of these, maybe. All right. And we have a full coordinate point listed, 5, 7. So, all right, so we've got a coordinate point for my initial value stated. And we have a rate. Yep. M equals 2. So if I want to know, again, if you want to make a story, this is at time 5, there were 7 people in Gamage Auditorium. And it was increasing by a rate of 2 people per minute, whatever this is, 5 minutes after the doors opened, whatever. And I want to keep track of how many people there were. Make up a story, reuse a story. This is some sort of positive rate of change of y with respect to x. So if I want to find some future value of y, final value of y, all I need to know is where did I start and how did that change? So we started at 7 and increased by 2 for any variation in x. So the variation in x, final minus initial, would be, final, our x minus our starting value of x. And there we go. So we've got And if you want to imagine this increasing here in this picture, why does it always jump? There we go. So I've just got a starting value here, a starting point here of 5, 7, and a slope, rate of increase, of 2. The y value changes by twice what the x changes at. So if this m equals 2, then the change in y is 2 times any change in x. Or how much however many minutes go by, the number of increase in the number of people inside Gamage Auditorium is twice that increase in amount of time, where I measure the time in minutes, maybe. So if you can see this, you can express these. You don't have to do any, we didn't need to do any computations. We didn't have to solve for something. All the information's already given. We can express changes in x and we can express changes in y without having to go through a full numerical computation or have a lot of numbers. But the more numbers we have, the more numbers appear in our expressions. Yeah?
Was your test, would you want us to change that to 2x minus 3?
No need to. This kind of expresses what's happening. So having it in this form, you can actually see the starting values or where we're talking about relative to initial values 5 and 7 for our independent and dependent variables. We're changing away from that at a rate of 2 y's per x, whatever the story might be. So yeah, just in terms of like forms for answers, there's a variety of equivalent algebraic forms for this. But the nice thing is you can just express, into this form automatically without having to compute anything. All right, so next time, test. Make sure you bring photo ID and a pencil. Make sure you're here on time so you get your full 50 minutes. If you're here a little bit early, you can even start bubbling your Scantron early. I'll be here. All right, study well, and maybe I'll see you at office hours.